Hello everyone. Today I'm going to present this paper, Efficient Greybox Fuzzing of Applications in Linux-based IoT Devices via Enhanced User Mode Emulation. And I'm the first author, Yao Wenzhen, and I'm now working in the Continental NTU Corporate Lab. And this is a collaboration work with the Institute of Information Engineering, CS, and the University of Chinese Academy of Sciences. And I'll give the introduction of this paper from the following 6 parts. The first is the introduction. And as we all know that the IoT devices are widely used in our daily life, and compared with the traditional IT vendors, the vendors of IoT devices pay more attention to system functionality rather than system security. So as a result, there are lots of vulnerabilities existing in the IoT applications, providing a large number of attack surfaces to the attackers. For example, in late 2016, the Mirai virus was developed to exploit the vulnerabilities of Linux-based IoT devices, which launched a massive DDoS attack to US. And there are also some other virus and attack events, such as the VPN filter and the Prowly, which also has a significant impact on the cyberspace security. And so it is important for us to detect vulnerabilities in IoT devices as quickly as possible. And among all these techniques, Greybox fuzzing is one of the most practical testing techniques to find the vulnerability in system and software. And it uses lightweight program and instrumentation techniques to collect the execution feedback of the program on the test, such as code coverage, to guide the entire testing process, which is very effective. However, the Greybox fuzzing techniques cannot be directly applied to the IoT applications, since the techniques lack of system and hardware support for executing the applications. So to solve these problems, existing Greybox fuzzing techniques use emulation techniques to execute the IoT applications. Here, the most widely used one of these QEMU emulators. And the QEMU supports two modes of emulation, the full system emulation and the user mode emulation. And the user mode emulation is attempt to execute a single applications. And the advantage is that it can execute application very quickly. But the disadvantage is that it still has some compatibility issues because it cannot execute the system calls or the execution context of the IoT application. On the contrast, the full system emulation can execute the entire embedded firmware, so that the IoT applications in the firmware can correctly execute it. But here the advantage is that we ensure the compatibilities, but the disadvantage is that it still suffers from the efficiency problem, since the full system emulation add virtual layers for emulations, so it would slow down the fuzzing execution speed. And here we confirm that the user mode emulation cannot be directly applied to the IoT applications by testing the 17 network applications in our evaluation dataset. And one of the cases is that the applications may report the error messages, such as some file cannot be found during the executions. And we also summarize the failure reasons as follows, and we will also solve these problems in our system. And to solve the both compatibility and the efficiency issues of the fuzzing process, there is an existing work called the Form AFL, which combine both full system emulation and the user mode emulation. And the workflow is like is shown in the figures. The user emulation part is trying to execute the common instructions. And when it executes to a system call, it will translate the execution to the full system emulation to handle it. So the system can guarantee both the compatibility and the efficiency of the fuzzing process to a certain degree. However, there are still issues. That's when there are a lot of system call existing in the target applications. The Form FL may translates frequently between these two modes, so that it will greatly slow down the execution speed of the fuzzing. So our system is trying to further improve the efficiency of the fuzzing and also at the same time guarantee the compatibility of the target applications execution. And the design goal is like this, that the applications in our system should behave the same as that in the full system emulation, and also the speed of the fuzzing should be as fast as possible. And the key idea here is that we set up the execution environment so that the system calls of the target applications can be directly passed to host machine. In this way, the target applications can fully execute in the user mode emulation, avoiding the overhead incurred by the full system emulation, which means that we only execute the full system emulations for one time to get the system resources that's required by the target applications. And the rest of the entire fuzzing process will be done in the user mode emulation. So it can guarantee the efficiency of the fuzzing process. And the R system equal AFL contains two major steps, the observations and the replay. The overview workflow is like this. We first set up the full system emulation, and it can execute the formal images and also the program the program we want to fuzz. And then we can observe in the full system emulation, that's the way the system resource that's required by the target applications, which include the launch variables, dynamic files, environment configuration, network behavior, and also the process resource limited. And we will obtain this resource in the full system emulations, and then provide it to the target applications by either deploy it directly on the host machine or instrumenting user mode cumulus so that the target application can get this system resource correctly and then execute as it behavior like in the real devices. And here we will skip the the techniques of this of the observation and replace approaches for these 5 system resources, and you can get the details in the paper. And in the implementation parts, we use the formula to emulate the full system emulation, and we also implement a system call detection so that we can correctly detect the start and the end point of the system call execution, so that we can retrieve the system resource correctly. And we also use the IDA-Pro and Beam work to do the reverse engineering works of the target applications we want to fuzz. And in the evaluation parts, we propose 3 research questions. The first 2 research questions is the same as our design goal. That is, we will evaluate the capabilities and the efficiency of our system compared with the state of the art. And we also will evaluate the ability of our system, vulnerability discovery ability of our system. And the experiment setup, we use 2 data sets. The first is the standard data set, which consists of the N-bench and the M-bench, which is used for the CPU and the system core performance evaluation. And we also use the real-world data set, which consists of 70 embedded formal images, which comes from the 3 famous embedded devices vendors. That is D-Link, TrendNet, and Netgear. And for the baseline, we select 3 baselines. The first is the original FL with which is integrated with the user mode emulation, and the FL full is FL fuzz engine with the full system emulation of Cumul, and also the state of art the form AFL. And in the configuration, we use the dictionary options in FLs. The keywords used as a dictionary token are collected through static analysis of target applications. And we also provide a normal network request as an initial seed for the our test applications. And for the compatibility evaluation, we first compared our system with the original AFL, and the results show that our system can correctly execute 16.6 out of 70 applications correctly. And for the original AFL, none of the application can correctly executed. And we also compare the system call trace with that in the full system emulation to prove the correctness of the target application's execution. And the results show that among the 36 applications in the success states, the majority of the application, the system call trace of the majority of application are identical with that in the full system emulations, and only a few applications behave differently. And in summary, the compatibility of our system is comparable to the full system emulation, and it's much better than pure user mode emulation, which means the AFL. And for the efficiency evaluation, we first compared with the original FL, and we found that for the standard dataset, bench and bench, the overhead is nearly the same. That means to test the common applications, our performance is nearly the same as the AFL. And we also evaluate on the real-world dataset and compared it with former FL and FL with full system emulation. And here we collected more than 1,000 seeds from HomeFast project to evaluate their running throughput. And the results show that our system performs much better than the former FL and FL in the fuzzing speed. So the summary is that our system enjoys significantly better efficiency compared to the state-of-the-art techniques. For the vulnerability discovery abilities, we use our system to find the real-world bugs, and the result shows that we find totally 10 vulnerabilities, including 9 0-day and 1 day. And finally, 6 vulnerabilities has been assigned with CVE numbers. And we also plot the unique vulnerability found over time in these 3 baseline, in the 2 baseline and our system. And we can find that our system can find all vulnerability faster than both firmware and AFL full system emulation, except for 1 vulnerability where our system and the former AFL tied. And in summary, the enhanced user mode emulation of our system indeed helps to boost the vulnerability detection capability of the Greybox fuzzer. So our system still has 3 limitations. The first is that our system currently only supports the Emulation hardware, and other customers customized hardware cannot be supported currently. And our system will have some issues when deal with some inter-process communications. And the third limitation is that our system can only find vulnerabilities in a single applications from embedded firmware. And the vulnerabilities that are spread across multiple applications cannot be revealed for now. So in a conclusion, we proposed efficient fuzzing framework for network applications in Linux-based firmware. And we evaluate our system on real-world applications, and the result shows that our system outperforms the state of ours in both capabilities and efficiencies. And we also found 10 vulnerabilities, including C7Es from firmware images. And in the future, we will support more customized hardware to improve the capability of our system. Thank you.